So here we're looking at intersecting planes, and in particular, finding the line at which two planes intersect. So to begin, we're going to be given two distinct planes. And the first thing that we want to do with these planes is make sure that they're not parallel. So we need to check if the planes are parallel. Now, how do we check if planes are parallel? Well, we identify their normal vectors and see if those normal vectors are scalar multiples of each other. And this, of course, is such that C is our scalar. Right? Because are parallel planes going to intersect? No! So we want to make sure that those planes are not parallel before we waste our time. So if you find that the planes are not parallel, then we can go ahead and find the equation of the line where these two planes are going to intersect. So I want to begin here by recalling the equation of the line in R3. So let's recall the equation of a line in 3 dimensions. So we know that the equation of a line passing through some point P naught. So we're passing through some point P naught defined by the ordered triplet x naught, y naught, z naught, and parallel to a vector v. And we know we'll define the components of this vector parallel to the line as a, b, c. We define the equation of this line using the vector valued function r of t, where we have the position vector x naught, y naught, z naught, plus that arbitrary parameter t multiplied by this parallel vector. So this is what we're looking for here. We want to find the equation of the line, this vector valued function r of t, where these two distinct planes are going to intersect. So let's go ahead now and establish some strategy for how to do this. So here we go. Here is a little strategy for finding the equation of the line of intersection between two distinct planes. So as we begin, I want you to keep the goal in mind. Again, the goal is to find the line of intersection between two distinct planes. So looking at our vector valued function for a line, we realize that we need two things. We need a point on the line. So we need to determine some point P naught that's on the line using just our distinct planes. We also see that we're going to need a parallel vector. And this vector is specifically parallel to the line. So that's our vector V. So that's our goal. We want this line of intersection. So we need to establish strategy for finding the point and a parallel vector. So here we go. Step 1. We need to find a point P naught on the line. So there's several ways to do this. One such way, my favorite way, is to find a point where the planes intersect one of the coordinate planes. So we want to find a point where the two planes intersect one of the coordinate planes. And you may be thinking to yourself, well, coordinate planes, aren't there 3 options? And you're absolutely right. There's always going to be 3 options to choose from. Now, you only need to pick one, but I want you to keep in mind all 3 options because oftentimes one will be easier than the others. So here we go. Your 3 options. The first option is to find the ordered triplet where the two planes intersect the xy plane. So here, we would go ahead and let z be equal to 0, and solve the resulting system for x and y. Another option is to find the ordered triplet where the two planes intersect the xz plane. Now in this case, we'll go ahead and we'll let y be equal to 0, and we solve the resulting system for x and z. And last but not least, our third option is to find the ordered triplet where the two planes intersect the yz plane. In this case, we would go ahead and we would let x be equal to 0, and we'll solve the resulting system for y and z. And now again, there are three options here, but we only need to pick one. So I encourage you to always explore the different options to see which case is going to be easier. Now, once you have that ordered triplet, that point P naught, we need to go ahead and find a vector that's parallel to the line. So as we begin here, I want you to recall the illustration that we looked at for orthogonal planes and how I pointed out that line of intersection. So what I want you to keep in mind is that the line of intersection exists on both planes, or it lies on both planes. So that means that the line itself is parallel to both of the planes and thus orthogonal to both of the normal vectors. So we want to keep in mind here that since the line L lies on both planes, this implies that this line L is orthogonal to both normal vectors. So it's orthogonal to both vector n sub 1 and n sub 2, those distinct normal vectors of the distinct planes. So, keeping that in mind, we also know that by the cross product, that the cross product of two vectors is orthogonal to the plane containing those two vectors. So in other words, we can say that the vector n sub 1 cross n sub 2 is orthogonal to both vector n sub 1 and n sub 2. Now wait a second. If L is orthogonal to both n sub 1 and n sub 2, and the vector n1 cross n2 is orthogonal to both n sub 1 and n sub 2, this means that the line and the vector defined by the cross product are parallel. So we can say that, therefore, by definition, the line L and the vector n sub 1 cross n sub 2 are parallel to each other. And this is exactly what we needed. We needed a vector that's parallel to the line. So we can go ahead and define the parallel vector v as the cross product of these two normal vectors, or the normal vectors of our two distinct planes. And so now we are officially ready to go. We have a method to find a vector that is parallel to the line, as well as three different options for finding an ordered triplet that's on the line. So we're ready. Let's go ahead now and look at some examples.